All right, today we are going to tackle one of the deepest, most mind-bending ideas in all of computer science. It's called the halting problem, and trust me, it reveals a hard limit on what our computers can ever hope to achieve. So let's just start with a simple question. Imagine you're a programmer. Could you, right now, write a single program, a master program, that could look at any other piece of code? I'm talking anything, from your favorite video game to the flight software on a rocket, and tell you with 100% certainty if it's going to finish its job or if it's going to get stuck running in an infinite loop forever.
I mean, it sounds like a super useful tool, right? A perfect bug checker. But the answer to this question, well, it's so fundamental that it did more than just inspire a new tool. It drew a hard, uncrossable line in the sand. It defined the absolute limits of what computers can do, and maybe more importantly, what they can never, ever do.
Okay, so let's get right into it. We're going to see how this simple, practical-sounding question leads to a truly mind-bending answer, an impossible boundary in the world of computing. So this is what's formally known as the halting problem. Let's break it down. You've got some program, let's call it P, and some input for it, we'll call that I. The big question is, can we build one universal checker program that takes any P and any I and always gives us the right answer? Either a clean yep, it'll eventually stop, or a definite nope, it's going to run forever. No maybes, no I don't knows. For every single program that could possibly exist. And here's the big reveal. The answer is a flat-out no. Back in 1936, the brilliant Alan Turing proved that a program like that is a logical impossibility. And let's be super clear here. This isn't a case of we're just not smart enough yet, or our computers aren't fast enough. No, he proved it cannot be written, ever. It's not a technological problem. It's a fundamental law of logic, baked into the very nature of computation. So to really get why this is impossible, we've got to step into Alan Turing's world for a minute. We need to understand the basic rules of the game he laid out for all of computing, before we can see how he broke them wide open.
You know, this whole thing didn't just come out of nowhere. It actually started with this huge challenge. In 1928, a mathematician named David Hilbert basically threw down the gauntlet and asked for a universal algorithm that could solve all mathematical problems. He called it the Entscheidungsproblem, the decision problem. Fast forward 8 years and Alan Turing comes along. But before he could even try to answer Hilbert, he realized he first had to define what an algorithm even is. And that's how he came up with his famous Turing machine. And here's the kicker. By proving the halting problem was unsolvable, he simultaneously proved that Hilbert's grand dream was totally impossible.
The real genius of the Turing machine is how simple and abstract it is. It's not a real physical thing with whirring gears and blinking lights. It's just an idea, a model. Think of it like a long strip of tape, a little head that can read and write symbols on the tape, and a simple set of rules. That's it. But here's the amazing part. That simple little model can simulate any algorithm you can possibly think of. The smartphone in your pocket, the most powerful supercomputer on Earth. Deep down, at their theoretical core, they're just really, really fancy versions of that one simple idea.
But Turing didn't stop there. He had another brilliant leap of imagination, the universal Turing machine. Think of this as a special Turing machine that can pretend to be any other Turing machine. And how does it do that? This is the crucial part. It treats the instructions, the program code, of another machine as just data. It reads the code from its tape just like it would read numbers or letters. This idea that code can be treated as data might sound simple now, but it was absolutely revolutionary. It's the foundation of literally all modern software, and it's the key that lets us build the paradox we're about to see.
All right, here we go. This is the main event. We're going to walk through the proof itself. And it uses this really elegant and powerful technique called proof by contradiction. The way it works is, to prove something is impossible, you start by pretending it is possible. Then, you just follow the logic until you end up with a complete, undeniable, absurd contradiction. It's like building a logical trap.
So, for the sake of argument, let's pretend. Let's imagine that this impossible program actually exists. We've written it. We'll call it H for halting oracle. And H is perfect. It can look at any program with any input and tell you exactly what's going to happen.
Our magical oracle, H, is pretty straightforward. It just gives one of two answers. It looks at a program and spits out either halt, meaning, yep, it's going to finish, or loop, meaning it's going to run forever. And the most important rule of our little game here is that we are assuming H is always right. No exceptions. Okay, now for the trap.
We're going to use our perfect oracle, H, to build a new kind of mischievous program. We'll call this one G. And here's what G does. First, it takes its own source code, the very instructions that make up G, and it feeds that code to the oracle H that lives inside it. So G is essentially asking H, hey, oracle, what am I about to do? Am I going to halt? But here's the twist, the absolute core of the proof. We program G to be a total rebel. Whatever H predicts it will do, G is specifically designed to do the exact opposite.
And this is the paradox in a nutshell. Think about it. If H looks at G's code and says, okay, G is going to halt, what does G do? Its programming kicks in and it immediately enters an infinite loop. But if H looks at G's code and says, oh, this G program is going to loop forever, what does G do? It's programmed to immediately halt. You see the problem? No matter what our supposedly perfect oracle H predicts about G, it will be wrong. It is forced to be wrong. It literally can never, ever get the right answer for this one specific program. But wait, our whole starting point was that H is always right. Well, we've just created a situation where it can't be. That's a contradiction. And when you hit a logical contradiction like that, it means your initial assumption had to be false. So our perfect halting oracle, our program H, it simply cannot exist. Checkmate. Now this isn't just some clever abstract logic puzzle. Proving the halting problem is unsolvable, that was like knocking over the first domino. And behind it was a whole long chain of other problems that came tumbling down. It revealed that entire categories of questions are fundamentally impossible for computers to answer. This brings up a really interesting and subtle point. In computer science, we say a problem is decidable if you can write a program that's guaranteed to stop and give you a correct yes or no answer. As we've just seen, the halting problem is not decidable, but it is what we call recognizable. And what that means is you can get a definite answer for the yes cases. If a program is going to halt, you can find that out by just running it and waiting. It'll stop. But for the no cases, the ones that loop forever, your checker program might just get stuck looping right there with it forever. See, there's this weird one-sidedness to it, right? We can always confirm that a program halts. You just wait for it to happen. Boom, proof. But how can you ever confirm that a program will never halt? How long do you wait? A minute? An hour? A billion years? There's no magic point in time where you can just give up and say, okay, I'm sure now. You can never be 100% certain.
And this idea gets even bigger. It leads to something called Rice's theorem, which basically takes the logic of the halting problem and blows it up to cover almost everything. What it says is that the halting problem isn't some weird special exception. It turns out that any interesting question you want to ask about what a program does, about its behavior, is also going to be undecidable. The halting problem is just the most famous example of a huge family of impossible problems.
And the consequences of this in the real world are just massive. Because of Rice's theorem, we know for a fact that we can never build a perfect tool that can look at any program and tell you, is it totally free of infinite loops? Nope. Do these two different programs actually do the exact same thing? Can't know for sure. Will this program ever print the number 0? Impossible to say in every case. Is this software 100% free of all runtime errors? We can never build a tool to guarantee that. These are all undecidable. And this has a huge impact on the day-to-day life of every single software engineer. They all work in the shadow of this impossibility. This is why software testing is so hard and so important. It's why we can't just build a magical tool that proves our code is perfect. It's not possible. So instead, we have to rely on good design, writing tons of tests, and doing code reviews, all because a perfect automatic bug finder is something we literally can never have. So, is that it then? Are we just stuck? Is this an unbreakable wall for all of computation? Well, maybe not. This is where things get really theoretical and, frankly, super cool, as scientists have started to imagine what it might take to actually compute beyond the limits set by Turing. So our computers today are basically universal Turing machines. They are bound by this rule. No way around it. But theorists have dreamed up other things. They invented the idea of an oracle machine. Imagine a normal computer, but with a magic black box attached that can instantly solve the halting problem. Sounds great, right? Well, the catch is, this new, more powerful machine now has its own, even harder halting problem that it can't solve. It's like you climb one level just to find a higher wall. Then you get into even wilder territory with hypercomputers. These are completely theoretical machines that would have to rely on some kind of undiscovered, exotic physics to actually break these rules of logic. And that really leads us to the final big mind-bending question.
Some physicists and philosophers look at all this and wonder, what if the universe itself is a kind of computer? And if it is it running on the same operating system as our machines? Is it bound by the same logical limits, the same paradoxes, or could the fundamental laws of physics themselves contain some form of hypercomputation, something that allows reality to do things that our computers can only and will only ever dream of? It's a heck of a question, connecting a problem from pure logic to the very fabric of our universe.